Hello, and welcome to this IBWave design release update for Release 13. In this release, we've made improvements to both beamforming modeling, and we've also added some updates to the 5GNR functionality. To start, let's take a look at beamforming modeling. Within beamforming modeling, we've added two major functionalities. The first is that you'll find that within our components, the components are now capable of being modeled as multi-beam components for both antennas and for small cells and other transmitters. This means that you no longer have to input, when designing an OEM modeling component, a full RF pattern. You can continue to do so, but at this point, you can also enter an RF pattern and information at the beam level. And I'll show you that right now. So what we have here is a small cell that has been adjusted to be a multi-beam beamforming small cell. Prior to Release 13, adding multiple beams onto a small cell was not a possibility. If you take a look at the electrical properties for this particular device, you'll notice that there are a few new fields at the bottom, an indicator as to whether or not this is a beamforming small cell. After which, what is the type of beamforming that this can be? In this case, it's an analog beamforming component. Now, in Release 13, most components, all components, will be treated as if they are analog components. Support for digital and hybridized beamforming components will come in later releases. But the point of putting it here is to make sure that once you do set this up, when we do add support for those features later, it will already be in your OEM components that you've designed. And finally, there's a field here listed as beamforming enabled. This is indicating that you are actually now interested in treating this as a beamforming small cell. So you'll set it to true. And once you do that, if you look at the entire band, you'll notice that I have a series of beams already listed. But if I right-click on this, I can now see the full coverage pattern, which is essentially the full beamforming pattern. And when I do that, this is the image that you would normally see as one combined pattern. But in this part, we've set it up so that each beam has its own RF pattern. You can do that now in Release 13. And when you do that, you can also specify the type of beam that this is going to be used for. And that will have an effect on the output maps that you have in design. So in this case, let's just take a quick look at just the synchronization beams. And you'll notice that the bottom beams here are defined as synchronization. Likewise, I can also filter this down to just a single beam. So if I want to see beam 1, that's the pattern for beam 1. So let's dig a little deeper into the beams. In this case, this small cell in the millimeter wave spectrum has 35 beams, and beam 1 has been defined to be a synchronization beam. I can define this beam to be more than just the synchronization beam. It could also be a PDSCH beam. PUSCH and the control setting, they are there for future use. In Release 13, they are not utilized, but as before, when talking about the beamforming type, we're offering you the capability to set up your components for the future functionality that will come in later releases. At this time, the synchronization beams and the PDSCH beams will be used in output maps in design. I'll be showing you that a little bit later. So, this is a synchronization beam, and with that, usually, you'll have a beam index. You can enter that beam index as well. You'll note that, as you saw before when I saw the individual patterns for each beam, that you have a pattern file for each and every beam. You can enter this for every beam type that you like. If you want, you can still join beams together. If you want to create a single beam of all the SSBs, you can do so. You can also do the same for PDSCH. It's up to you. You have that flexibility. Okay, so now let's take a look at antennas. It's not just small cells that are multi-beam. It can also be a standalone antenna. And I'll show you that configuration right now. So when it comes to designing components, it's not just small cells that are multi-beam components that are available for beamforming. It can also be antennas. Or if you wanted to separate out the antenna from the actual signal source, You could do so by building an antenna that you want to be a multi-beam antenna. And the same principles apply to what you saw in a small cell, except we've added a little bit more flexibility here. You'll notice that there are two separate connectors here, connector 1 and connector 2. The same properties exist when you look at the electrical here. You'll notice that we have a beam forming enabled as true and a beam forming type. Where things get a little bit more interesting is within the band itself. So here, under band 1, I have those same connectors listed for this frequency range, and I have a series of beams. The same definition of beams exists as what you saw in a small cell. You can set up a beam type, you can set up the beam index, and you can also put an individual pattern for every beam. But where things get interesting is in this connector. You saw before that there were two separate connectors, 1 and 2. What I could do within an antenna is start to associate more than just one beam and RF pattern for these connectors. Previously, every beam that we had in our multi-beam antenna was really a separate connector, but that doesn't really reflect reality that well. When you look at these new components, you'll now be able to associate 10, 12, as many beams as you like with different directions onto each connector. And what that lets you do is that you can now change the RF pattern that you might have for this antenna. In 5G components, antenna panels can have subarrays, and you need a way to represent those subarrays, which have different RF patterns, different beam IDs, and you can do that in this context by associating each of those patterns with a connector. So that means that beams 1 all the way to beam 16 is connector 1. Whereas if you look at beam 17, from beam 17 to beam 35, those are all connector 2. And within those two contexts, I now have a way to connect a cable to connector 1 and get a certain beam pattern, or I can create a subarray and call it connector 2 and connect a cable to that and get a different set of patterns. This is the capability we've added into multi-beam antennas. So now let's take a look at what this looks like in design. So here we are within design. I have a 5GNR setup, very simple one, but just to demonstrate what these beam types will look like in design. When I've selected my component, you'll notice that within the properties section, under the band itself, I have a beam number. These beam numbers now also indicate what the beam type is. It'll show me the beam type, and it'll show me the SSB index as well, if that's relevant. So let's take a look at beam 8. Beam 8 is a hybridized beam. It's now both an SSB and a PDSCH. Why is that important? Well, that's where the output maps come in. In Release 13, we've updated output maps to take beam types into account. I'll show you that right now. So here we are in this exact same design. I'm looking at the output maps that I've created, and I now have an additional one. I have PDSCH RRP, and we also have the SS RSRP that you're used to. The main difference is that once you're using a beam forming component, and once you've defined the beam type, the SS and the PDSCH start to make a difference. SS RSRP, SS SNIR, and RSRQ will now run on the synchronization beams that you've configured in that component. What you're looking at here is those synchronization beams. If I were to switch to PDSCH, at that point it's using the PDSCH beams that I've defined. And the output maps could be different depending on what you've configured within those beams. You can also specify the powers now within your bandwidth part to adjust these individual powers. That's one of the benefits of using this. And it also gives you an opportunity to start playing with the actual beams as you go. So what kind of things can I do live as I'm predicting? Let's say I don't like the configuration that I have right now. I could go into the component and start to change the beams. But let's say I wanted to see what the prediction was like, just changing one of the beams to be disabled. Within this same properties area, I see a beam enabled. Here, I can set that beam to false. I can now start disabling individual beams. And once I do that, I'll end up with various results when I actually run the output afterwards. So I'm going to run the output and show you what it looks like. So this is my before view. I'm going to go and disable a few of the beams, and then you'll see what happens as an after once I've run the prediction and have adjusted the actual component to start disabling some of those beams that I don't want to see. So here's an after picture after I've replaced 3 of the beams by essentially disabling them. So let's take a quick look at that. Beams 1, 2, 3 are disabled. Beam 4 continues to be enabled and still is acting as an SSB beam. This results in an updated output map. If you want to run any scenario that you like, disabling edge beams, or maybe using different configurations of beams, you can do so on a component level. You can do this en masse by essentially selecting each cell that you'd like to change, going to the properties, and adjusting the beams for these together. You could create separate components if you liked in order to simulate that, or you can do it live in the application. This is the benefit of beamforming components as they are being created and utilized within design. So now let's take a look at the generalized 5GNR updates we've made since release 12, part of which utilized these new beamforming components, and others are just updated output maps that would be of interest to anyone doing a design of a 5G network. In this particular network, you'll notice that there are a couple of new output maps, but let's take a look at them in this list. The first one that you'll notice is PDSCH-RP. This new output map utilizes those beam types that you've specified into your components. If you didn't specify a beam type, or if you're upgrading from release 12, then this output map will essentially run on all the beams that were previously defined. Without a beam type, we assume that everything is an all beam type. That ensures that anyone upgrading won't see a change in functionality just because we've added these new beam types and new maps. However, if you have entered a PDSCH beam type, we will now target output maps to those beam types. The same situation goes for the SS output maps. We've added a new RSRQ output map, but in addition to that, the SS maps will now run on your SS beams. This is important to create that differentiation between the two. Your SS beam type and beam pattern is different than your PDSCH one, and you can view output maps related to each of those beam types you define in your components. Additionally, on top of those new output maps that run on each beam type, we've also added capacity and the dominance over macro. Let's take a look at capacity. Capacity is now running as you would have expected in the same sort of algorithm that you saw in LTE and prior. This is all based on your usage profiles that you define in that network space. In this network space, for example, I've defined that the usage capacity requirements are that there are 50 people on the 4th floor and the usage profile is office. What does that usage profile mean? In this case, the office profile is such that they are using 12 megabits per second in that space per user. And these capacities that you see here as green indicate whether or not users within that space will be able to access and pass a capacity test based on that profile. You'll notice that some places are marked as no service. That's for good reason. When you talk about a millimeter wave network, the network may not reach those areas, and that can be evidenced by looking at the overall SS RSRP and PDSCH RSRP maps. When you look at those, you'll notice how the capacity is related to the coverage. So another thing that was requested recently was to ensure that the handoff matrix was listed. So let's take a look at the 4th floor. In the 4th floor, I have 2 different sectors, so 2 different types of small cells serving the same area overall. Now, if I were to click on the handoff matrix button, I will get a listing of what the coverage is for those people in particular sectors. So as I said, there are 2, 4, and 5, and you'll note that some handoff will exist between the two depending on the coverage in particular areas of that office. One important note when it comes to beams and beam types. If you remember, I said that PDSCH and SS will now run on their respective beam types. The max achievable data rate is a function of what happens in the PDSCH space. So once you've defined your beam types and essentially have also created PDSCH beam types, the MADR values that you see are related to the PDSCH beams. This is something that you'll notice in Release 13. And again, for anyone who's upgrading from Release 12 to 13, if you haven't specified any beam types, you should not receive any change in your behavior or output maps. It's only once you've started to add beam-forming components that you'll start to see these variations in the output map depending on the beam type. One additional housekeeping item that you should be aware of. I mentioned before that the handoff matrix is there. The handoff matrix is dependent on thresholds and margins. Under your project properties, in network optimization and 5GNR, you will now notice that there are new threshold margins here for the different signal types. These are used in your calculations of your handoff matrix. Adjusting these will adjust what you see in those tables. These are all default values, and of course, you may update them, and it is to your benefit to do so if you want to create different scenarios for handoff. So let's recap what's happened in Release 13. You can now create beam-forming components for both antennas, small cells, and other transmitters. When you do this, you can now add an RF pattern for every beam. Additionally, you can specify the type of beam as SS or PDSCH and add an SSB index. Within antennas, you can now create subpanels, each tied to a connector. You can add multiple beams, which means multiple RF patterns to a single connector, and then create additional connectors to simulate different kinds of configurations of your panel, either with more power, fewer beams, whatever you like. In design, once you've used one of these multi-beam components and specified a type of beam, we will begin to target our output maps to those beams. This is just the beginning of beam forming. In Release 14 and onwards, we will extend this out to include other beam forming types and to move to a more dynamic approach of being able to adjust powers and so on by particular beams. This wraps up our look at Release 13 and its focus on beam forming and 5GNR. Thank you.